Okay, so here we go. Last time we were talking about directional derivatives. Remember, the big idea here is that it's really just a rip-off of the idea of a partial derivative. In fact, case could be made they are partial derivatives. Remember, when you have a coordinate system set up, right, you're talking about something physical like this room that we're in. You know, we arbitrarily will set, axes, definition of our coordinates for some sort of convenience, but it is arbitrary, even if it is convenient. And so if you want to talk about a unit vector that points in a different direction, fine. Any unit vector can be a standard basis vector and thus part of an axis system that defines coordinates in whatever world you're talking about. So any unit vector will do. Effectively, partial derivatives were just a special case that we were narrowly looking at because we arguably kind of forgot that our coordinate system was arbitrary. Okay. All right. So any unit vector, and you can define this thing called a directional derivative. There's the notation. There's the definition. There's a handy formula for computing it. And here's a couple of interpretations. It's going to give you slope of the graph. It's also going to be a multiplicative factor. You know, what you multiply by input change to get output change. Okay, so this is where we left off. I want to point out one thing in particular. This point of view, this interpretation as a multiplicative factor. Keep in mind the input change that you're going to multiply by is either a displacement in a certain direction or a speed in that certain direction, right? And then the resulting output change that you get, likewise, in the target is either a linear estimate of change or a speed in the target. So now, just from a notation point of view, right? What should we call the thing that we multiply by ds to get df, or the thing that we multiply by ds dt to get df dt? Well, it's a pretty easy pitch that maybe we should call that thing df ds. I think this is a lovely notation. It kind of gives you an alternative point of view on how to think about a directional derivative. It's rate of change of the function with respect to distance traveled. Right? Now distinguish that from rate of change with respect to time. After all, time, it depends on how fast you're going, right? If you're moving really fast, then sure, the function's going to be changing fast. If you're moving really slowly, the function's not changing much at all. It all depends on yourself, right? But rate of change with respect to distance is more of an absolute. It doesn't depend on, momentary particulars, such as speed. Okay. All right, so it's another nice interpretation. Okay, example. So let's suppose that you have a function given. You're going to look at the graph of that function, and the question is to find what is the slope of that graph. Now, specifically, we want to know the slope at a certain point and in a certain direction. Okay, now had this direction been a coordinate axis direction, then we would just say partial derivative, and that would be a super easy calculation. Well, it's not a coordinate direction, but it remains that slope of a graph is a directional derivative. After all, directional derivatives basically are partial derivatives just with respect to a different coordinate system. Slope of the graph, directional derivative. Compute, plug and chug, not that much to it. Easy to compute the gradient. Right? Take various partials, plug in the point in question. Right? That's just easy computation. One little subtlety that students do sometimes get wrong. Notice in our definition up here, coming back up to it, in our definition here, and I'm going to pick a different color. Specifically, we require that this be a unit vector. After all, we want to be able to talk about how this other vector, this unit vector, I need to be able to view it as being a standard basis vector. Right? So it has to be a unit vector. in order to be able to sort of piggyback off of all of what we already know about partial derivatives. So we can only talk about directional derivatives, as defined in this book, if we're talking about a unit vector, and notice that what was given is not a unit vector. Notice further, it says direction of the vector 3, 4. Vectors, we write them with coordinates because it's convenient, right? But ultimately what a vector is a direction and a magnitude. So when we say the direction of the vector, what we mean is, look, there's a direction, there's a magnitude. We kind of want to get rid of the magnitude, right? So we divide by the magnitude. Said differently, we describe directions with unit vectors. So all we have to do is just find a unit vector that points in the same direction that this given v points. And again, easy calculation. And that direction is this unit vector right here. How we doing? Everybody okay? All right. Now, let me show you where there's a kind of a landmine in this question. This is an easy misinterpretation to make. It is, however, a misinterpretation. Let's see here. I'm going to zoom so I can draw this picture here. Let's see here. I'm going to draw an axis system like this. And let's see here. We are at the point 3, 1. All right, let's draw 3, 1. There's 3, 1. And it says, now in the direction of the vector 3, 4. Okay, so 3, 4 is a vector that's about like that. Right, so the direction of 3, 4, remember we agreed that the direction means the unit vector in that direction, something like that. Okay. Here's the misinterpretation. Some students will look at this phrase, in the direction of the vector 3, 4, and think that this means toward the point 3, 4. Right, so very importantly, it does not. Right, direction is part of the definition of what a vector is, and if there's a vector given, then we mean that direction that is part of what that vector defines. Right, so not toward the point 3, 4. After all, the point 3, 4 would be about right here. Right, position vector being the same as the purple actual vector. So this point 3, 4 is like that, and then mistakenly viewing this as toward 3, 4 would have us going that way, and that's wrong. So do be careful with that misinterpretation. Again, the word direction is a special word. It's part of what makes up a vector, so that word direction means you're interpreting it as a vector. Does that distinction make sense? Does anybody have any questions about that? Okay. All right. Okay, so heads up for that. Okay, let's see. The next example is, frankly, pretty similar. I'm going to go through this one also pretty quickly. Slightly different scenario. Here we're looking at temperature as a function of position. Again, given function. And again, we're at a certain point, moving in a certain direction. Again, it's not a unit vector divided by the magnitude to make it a unit vector, just like the previous. Right? The difference is that in this case, the question asks for dTds, rate of change with respect to distance. And as we saw on the previous page, again, this is one of our primary interpretations of directional derivative. Right? That's what the directional derivative gives you. How much is the function changing per unit distance traveled in the direction of your given unit vector? So again, formula with the dot product of the gradient. Right? And then again, you have to compute the gradient, take the various partials of this function. By the way, good little exercise. Right? Make sure that you're comfortable with what I get down here as a result. Make sure you can do that. You compute the gradient, you do the dot product. You don't forget to take your given vector and understand the direction of that vector by the corresponding unit vector. And everything else is arithmetic. What do you think? Everybody all right with that? Okay. All right. Okay, now a slightly awkward, I'm going to call this a cultural point. And that is, there are some contexts. Now, not this course, so I emphasize, right? Not us. In this course, we're going to stick with the book on the convention that I'm about to address. But outside of this course, and y'all will eventually be out of this course, right? In some other context, some people like to remove the requirement that the vector be a unit vector. Now that's a question about, it's very concerning, right? The argument that we've made here was that, hey, any unit vector could be a standard basis vector if you just set up your coordinates accordingly, right? And blah, 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 partial derivatives. If you're giving me not a unit vector, that seems like it should matter, right? And it does. So I want to point out, I'm going to go back to the where we were here and clean up this big mess. And I'm going to adjust how this works. So recalling, if you have a unit vector, then the directional derivative is denoted like that, defined like that, computed like that, and it's the slope of the graph, and it's a multiplicative factor, aka df/ds. If you remove this requirement, as some people like to do, you could still call it a directional derivative. You can still use this notation. This definition still makes sense. This formula here still works. The only thing you lose is you no longer get these interpretations. You no longer get that this alternative definition of directional derivative. It no longer computes slope of a graph. It no longer computes this multiplicative factor df/ds. But those who like this choice would point out this is still a pretty natural thing to want to compute. Maybe I'm not interested in how fast the function's changing with respect to distance. Maybe I'm actually in my car driving down this road and I am moving with an actual speed, and I want to know literally how fast is the function changing per unit time. And this still totally gets right on that. This is exactly what that is. This formula is still really convenient for computing that. This is still a useful idea. And again, taking it further, not only is this still kind of useful, one could argue it's even more useful because, again, we've gotten rid of this liability, this restriction that our idea can only apply to unit vectors. What a restrictive requirement. Only unit vectors, right? Case could be made, it's much more powerful applying to all vectors. So there's really no magic right or wrong answer on the sort of the dispute on this convention as to, should we require it be a unit vector, so I get these nice interpretations here, or should I relax that convention and therefore be able to apply these ideas much more broadly at the cost of these interpretations. So the reason I bring this up is because you never, outside of this course, you never really know which school of thought the person you're talking to subscribes to, right? So it could go either way. By the way, outside of this course, I kind of put myself in this other school of thought. I kind of don't like the unit vector convention outside of Math219 for most of the reasons that I've just enumerated. But that said, very importantly, in Math219, we do require that the vector be a unit vector. The word directional derivative only makes a sense if the vector in question is a unit vector, and as such, we get all of these interpretations as we've previously discussed. I just want you all to be aware, again, outside of this class, in your engineering or scientific or whatever futures, that be aware that different people take a different point of view on this. And always be heads up, please. Always take an active role. If someone says directional derivative, are you a unit vector kind of person, or are you a not unit vector kind of person? And otherwise, you might have a miscommunication. Okay. Alrighty. Moving along. Here is a very natural question to want to ask. Suppose you have a multivariable function. Real value, multivariable function, differential. And suppose you're standing here in the domain. For the purposes of this example, my own personal preferred scenario is I'm out in the woods, and that's me, and I'm trying to entertain the question of which direction I should walk. And I emphasize direction. So again, unit vectors, right? I'm going to think about all possible unit vectors representing directions and directions only that I could walk from this point where I actually am. And in particular, I want to know which one is going to make the directional derivative. And keep in mind, now pausing before I finish that thought, directional derivative says that as I move in the domain in a certain direction, what's the rate of change of the function? Right, df/ds. Reasonable question, which one is going to maximize that output rate of change? Of all these different input unit vectors, of all these different directions I could start walking, which one maximizes the rate of change? So in particular, I could imagine, this being February, maybe it's cold outside, and I'd like to know which direction do I walk to make it warmer. I'll go any direction, just which direction do I go to make it warmer as fast as possible? Plausible? Okay, so that's the question. Now, before I get to an answer, I want to talk a little bit about terminology. These directions, and let me go ahead and assume that I know what the answer is. Let's suppose that this is the answer. What term should I use to describe this direction? And do keep in mind that the directional derivative has different interpretations. On the one hand, directional derivatives are df/ds. How fast is the function changing? Okay. On the other hand, the directional derivative can be thought of as the slope of the graph. Right? Okay, well, with that in mind, this direction that I come up with, I mean, depending on which one of these interpretations you take, you can describe that direction different ways. The direction that makes the rate of increase of the function as big as possible means that it's the direction that makes the function increase as fast as possible. Isn't it reasonable then to call it the direction of fastest increase? I think it's a perfectly reasonable point of view. Now, alternatively, also perfectly reasonable, if you're thinking of the directional derivative, the thing that you're trying to maximize as being slope, keeping in mind that slope is a measure of steepness, keeping in mind that I'm going to be walking in whatever direction is the steepest, which means I will be climbing that hill, right? And if I want to know which is going to make me ascend the hill in the direction that's as steep as possible, then okay, well, steepest ascent. pretty reasonable point of view as well. Take your pick. For whatever it's worth, I have a slight. I didn't mean to do that. Let me leave that there. I have personally a slight preference for this term right here, direction of fastest increase. I'll explain why. Direction of fastest increase makes sense in any setting, no matter what kind of a picture I've drawn. Talking about the direction I go to make the function increase as fast as possible always makes sense. It doesn't depend on your picture. Whereas, tragically, if you think about it, this one does. Direction of steepest ascent suggests you're thinking specifically about the graph. Because only if when you're looking at a graph is the vertical axis actually describing the value of the function. Right? And only then is your picture that you're looking at actually, like for example, a hill. Right? So this terminology, direction of steepest ascent, sort of assumes that you're thinking of the function in terms of its graph. And maybe you are, but you might not be. In fact, you need not be. In fact, you sometimes can't be, right? And I think that makes this really awkward. So my own preference is the term direction of fastest increase. It always makes sense no matter the context. This direction of steepest ascent only makes sense if you're looking at a graph, and otherwise it's kind of awkward. And the frustrating thing for me about this is that the term that I don't as much care for is the more popular term. And you're going to see this around most of the time. People talk about the direction of steepest ascent. In my class, you're going to hear me talk about the direction of fastest increase. Same thing, different terminology. Okay. All right, so let's answer the question. What is this direction of fastest increase? All right, so, okay, well, whatever vector I choose, I want to make my directional derivative as big as possible. My directional derivative is computed with a dot product. Dot products are computed as magnitude times cosine of the angle between them. Keep in mind, we're talking about these v vectors being unit vectors only, so this entire magnitude here is just 1. So we can throw away that factor. Doesn't do anything. So really, the thing that we're trying to maximize, and keep in mind, we're trying to make that as big as possible. Effectively, then, that means that we're trying to make this as big as possible. Wait a second. The magnitude of the gradient, constant. The magnitude of the gradient is constant because we have not yet started moving, right? I'm still standing there in the woods. Here I am standing in the woods, and I'm thinking, I don't know, should I walk that way? Should I walk that way? Should I walk back that way? I haven't moved. The gradient only depends on where you are. It doesn't depend on which direction you're looking. It doesn't depend on what you're contemplating, right? So that's not changing at all. So that's a constant. So if you want to maximize your directional derivative, you can do so just by you can do so just by maximizing cosine theta. Right, keeping in mind that we're talking about the gradient being dotted with our yet to be determined direction vector v, cosine theta. That's what I want to make as large as possible. And that's easy to do. If I want to make cosine theta as big as possible, I just need theta to be 0. That means I need this angle right here, the angle between my two vectors here. I need that angle to be 0. That's easy to do. I can accomplish that just by choosing that unit vector that points in the same direction as the gradient. In other words, the gradient divided by its own magnitude. What do you think? Everybody buy it? So it's a really neat answer to the question. And by the way, this always works. It's really handy. If you want to find the direction of fastest increase, aka the direction of steepest ascent, that direction of fastest increase formula. Unit vector pointing in the direction of the gradient. Okay, nice, crisp, little convenient answer. Okay, now let me ask a related question. Keep in mind my whole goal here, right? Given a direction, given all my options of directions, I wanted to make this directional derivative as big as possible. I found how to do this. I found this vector that makes this as big as possible. Okay, how big is it? If it's as big as it can be, how big is that? Okay, reasonable question. And easy to compute because, again, the thing I want to know how big it is, directional derivative, computed with a dot product. The vector v is gradient divided by the magnitude of the gradient. Gradient dot itself is magnitude squared. And so the nice convenient punchline is that the magnitude of the gradient is the answer to that second question. Is that cool? Straight up computation. What I think is nice about this pair of questions is that the answers are both kind of, in some sense, they're both the gradient. What direction should I go? Well, whatever the gradient says. What's the directional derivative in that direction? Oh, okay, well, the magnitude of the gradient. Gradient's the answer to both questions. And I like to phrase that, as I have on the next page here, I call this a geometric characterization of the gradient. And let me remind you why this is news. The gradient, as we've previously studied it, where did it come from? Right? Let's just, thinking back, we came up with this idea of a gradient as a notational convenience. We were writing down linear approximations. I had a bunch of terms in there, ... It was really clunky to write that down. And so we just kind of made up this shorthand. It was just notation. Now we see that it is a geometrically natural thing. The gradient is the vector whose direction and whose magnitude are these natural things. The direction is the direction of fastest increase. The magnitude tells you how steep is the hill. What's the directional derivative in that direction? So I call this a geometric characterization because notice now we're understanding the gradient vector by way of its geometric features, not by way of its coordinates. That's algebraic stuff, right? We're understanding it now by way of its geometric elements, you might call them, the direction and the magnitude. So I think it's a powerful sort of reconception of what a gradient really is. Okay. Is everybody happy with that? Okay, let's see an example of this in action. First, a point of lingo, notation, however you want to say it. So we have a hill that's in the shape of the graph of a function, and in particular, this hill looks like that. Keep in mind when you're talking about a hill being the shape of a graph, that just means that the function is telling you altitude as a function of longitude and latitude. Okay, now that being said, there's a couple of different ways that I could reasonably understand where I am, my location. Right? Now the obvious way to understand my location is, well, there I am. I'm standing right there on the hill. Point on the hill, it's a point on the graph. It's a point in 3 dimensions. Right? Here's the other practical, convenient, common way to describe location, and that is with map coordinates, right? So typically longitude and latitude. And if you describe your location with longitude and latitude, 2 coordinates, right? Nobody ever tells you where they are by longitude and latitude and altitude above sea level, right? It's kind of understood you're on the ground, typically, right? Unless if you're flying in the air, I suppose you give the altitude also. But if you're standing on the ground, it's understood. Well, yeah, of course I'm standing on the ground. Now, I'm not 300 feet beneath the surface of the hill. Of course I'm on whatever the height of the hill is. Okay, so the unfortunate, arguable sloppiness is that very often we'll conflate these two things, right? So I could easily say, okay, yeah, you're at the point X, Y. Well, I don't mean you're there. You're obviously on the graph above the point X, Y. Right? It's very common, and it's just very convenient. And I don't think there's any actual confusion here, because what else could I have meant by the point X, Y? Does everybody see what I'm talking about, and how this is really not worth being fussy over? Now, I did in this example, I was careful in how I phrased this. I talked about, okay, I'm at the point sitting above 1, 3, right? So I specifically addressed the distinction in this example. That was weird. I'm usually not going to do that, and most other people won't either, and you won't see this on exams, I wouldn't think. So that means that it falls to you to be prepared for this, and to understand that a point in the domain is a sloppy but convenient way to describe a point on the hill. But then you have to interpret appropriately. Okay. All right, let me pause on this for a moment. Is everybody okay with this blurring, this sloppiness? Okay. So, yeah. The question says, which way is uphill? Well, previous page tells us that uphill, namely the direction of steepest ascent. We are, in fact, looking at a graph here, so I can say direction of steepest ascent, direction of fastest increase also. Directional derivative is the thing I want to maximize, and the gradient is the way that we maximize it. So we compute the gradient, we plug in the point in question, and this then, let's see here, let me do it like this. Right? This is the direction that points uphill. And if I wanted to be careful and fussy about this, I could say, we really should divide this by its own magnitude so that it's a unit vector, but whatever. This is pointing what I'm going to call southwest. And by the way, real quick, it is conventional, not uniformly, but to use, my pen just died, to use the positive y direction as north. So if the positive y direction is north, then you can see this is pointing southwest. Is everybody okay with that? Everybody's happy? Okay. Let me plug this in real quick so it doesn't... I might be able to use this later. Get the little thing off. Sorry. Okay, let's see here. Sorry. There we go. Okay, now next question. How steep is it there? How steep it is, of course, is just what is the value of the directional derivative in that direction. And the value of the directional derivative is the magnitude of the gradient, which is just a little under 3, which means this is a very steep hill at that point, right? The slope is almost 3. It'd be something like this. That's pretty steep. Everybody all right? Okay. Moving along. Okay, so it turns out that gradient vectors also connect in a powerful way to level sets. This kind of comes out of nowhere. It's unexpected, but it's really cool how this works out. So let me just walk you through it. Here is the scenario we're going to consider. We have a differentiable function, blah, blah. We're looking at a level set of that differentiable function, so where the function is equal to a constant. Keep in mind, that means that on this entire surface, the value of the function f is always the same constant c over this entire surface. That's what a level set is. Okay, so I'm going to make the observation that if I were to move in the direction of a tangent vector, any tangent vector, doesn't even matter which one, something really nice happens. In particular, as I move in the direction of any one of these tangent vectors, and just for mess purposes, let me just pick one, and I'm going to zoom so I can draw better. Okay, so there's my tangent vector. I am actually moving, therefore, along the set itself. So maybe I start there, and maybe I do something like this. Right, now this dark blue path that I've just drawn, this represents a path that is entirely within my surface. Every point I'm on the surface for the entire time, and notice that when I get to this point A, my velocity is a tangent vector. And I propose, I think pretty believably, that any tangent vector can be thought of as being a velocity vector for some curve that is entirely within our surface. That seem pretty believable? Yeah? All right, now let me ask how fast is the function changing as I do this? You know, as I move along the curve, or said differently, when I'm at this point and moving with that velocity, which I am as I'm moving along this curve, how fast is the function changing? Well, at this point, the value of the function is c. At this point, again, still on my surface, the value of the function is c. At this point, again, c, right? Along this entire curve, every point on this whole curve is on the surface where f is always c. So, kind of follows then that when you're at this point and moving with this velocity, the function's not changing. The directional derivative is 0. Anybody buy that? Neat fact, if you're moving tangent to a level set, the directional derivative is 0. Okay, so let me come back to where I have this stuff documented. So I'm going to clean up my mess here. Okay. So yeah, as I move in that direction, my directional derivative is 0. Keep in mind, directional derivatives are computed with a dot product with the gradient. That means that this dot product is 0. Right. Dot product is 0. This means something geometric. When a dot product is 0, that means the vectors are orthogonal. So this is a pretty neat conclusion that I get here. Not only when I am moving in the direction of a tangent vector, not only is the function not changing, but I'm also perpendicular to the gradient. And now let me remind you that this works for any tangent vector. Right? So for any tangent vector to this surface, every tangent vector perpendicular to the gradient. And I claim there's really only one way that that's possible. If you have a gradient vector, this is a better drawing here. If you have a gradient vector that's perpendicular to every one of these tangent vector, perpendicular to every tangent vector, then it's perpendicular to the surface. And that's the really cool fact. That's the really nice punchline. I can get this thing to move. Come on, here we go. So gradient vectors. Okay, gradient vectors are always perpendicular to the entire level set. At the point where the gradient's computed. Everybody buy it? Okay. So let me flash you back now real quick. Remember, there's different ways to represent functions, and depending on whether you're looking at a graph, or whether you're looking at a level set, or whether you're looking at the image of a parametric curve, right? These are all different contexts. Calculus looks different in all of these contexts. You have to be very, very careful to keep your calculus interpretations separated and appropriate to what kind of a picture you're actually looking at. What we have here is one of the biggest facts of what I like to call the calculus of level sets. If you want to understand calculus, gradients, of course, are part of calculus. This is a kind of a derivative of sorts. Calculus, in the context of level sets, this is a pretty big interpretation. Gradients are always perpendicular to those level sets. Okay. All right. So let me show you an example of where this is useful. This is something we've already talked about, but we talked about it from a different point of view. We talked about how if you have a tangent plane, let's see here. Here's my original surface. This surface is a graph of a function f. And if you want to find the equation of the tangent plane, well, we know how to do that. What you do is you realize this function, f of x comma y, can be linearly approximated. You compute the linear approximation. The tangent plane then is the graph of the linear approximation. So this tangent plane, you get by way of, again, there's a fair amount of calculation that goes into that. Just into making sense out of linear approximations, right? Okay. Here's a different point of view. Now, this is a really nice alternative point of view. Nice alternative point of view. Remember, we've noted this before, that whenever you have a graph, as we do here, right, we're looking at the graph. This surface is the graph of our function f. Every graph is also a level set. So all you gotta do, it's this one little trick of just, take that term and subtract it over to the other side. Hardly anything happens algebraically, right? But perfectly equivalent. Nothing happened. We can now realize this as being a level set of a new function. So I don't have to think of this as being a graph and take a graph point of view and use the calculus of graphs. I don't have to be all graph heavy on it. Instead, what I can do is just reinterpret it now as being a level set. It is a level set. It's a level set of this new function g. And once you understand it as a level set, well, we have ourselves a pretty powerful tool here. Any level set, whenever you're looking at a level set, you want to find a vector perpendicular to that level set. Cool, gradient. Nothing to it. Okay, great. Well, let's do that. Again, forgetting about all this graph stuff. We're looking at a level set of g. I compute the gradient. Easy calculation. That gives me a vector perpendicular to my level set. Oh yeah, which means that's a vector perpendicular to my tangent plane. That means I can use this as my normal vector. and now it's all over but the shouting. Once you have your normal vector, then of course that normal vector figures very prominently in the equation for a plane, and yada 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 details. Y'all can. In fact, I encourage y'all to take the moment or two that it'll take you to think it through to this point, do the algebra down to this point, and confirm that in fact you get this familiar equation for the tangent plane. Graph of the linear approximation. So just a different point of view of how to get that same result. How are we doing? Is everybody okay? All right, this example I'm going to show you is pretty boring. I'm going to be very quick about it because it's really just, step for step, exactly what's on the previous page. The question comes to us as we're looking at a graph of a certain function, and we want to find the tangent plane. And the very first step is to take what came to us as a graph of one function and, just like we did on the previous page, reconceive of this as being a level set of this other function. And once you have this new function here, right, this thing called g, whose formula is the left side of this equation, that's the thing I'm viewing it as being the level set of, then you just take the gradient. You evaluate at the point in question. That gives you your normal vector, and then thus your equation of your plane. Now, only the tricky part of this is, again, reinterpreting a graph as a level set of a new function. And once it's at this point, we know the gradient's perpendicular. We can use the gradient as a normal vector. It's all the same. How we doing? Everybody okay? All right. Okay. So let's see here. I have no idea how much time I have because that clock can't be trusted. Let's see here. I have 2.5 minutes. All right. Let me go back to this. I just want to set the stage for the next thing we're going to talk about. We're going to talk about something called the implicit function theorem. Some of y'all may have seen implicit differentiation in the past. My best guess is that what you saw for implicit differentiation was treated sloppily because by the way, I'm not going to treat this rigorously. This is not a class about rigor, right? But a less sloppy, a plausibly, reasonably tight presentation. It requires tools that single variable calculus courses don't have. And so this is our first opportunity to clean that stuff up. So a couple different ways you can view the question. On the one hand, you have a curve, and maybe you're viewing it as being a level set, aka you're viewing it as being the solutions to an equation. But I want to know, can I view this as a graph? I want to know, can I solve for y as a function of x? And notice in here, y is not a function. Right? In this equation that we're given here, y is an input variable, just like x. It's not a function. I can't just declare it to be a function. What if it isn't? Probably isn't. Doesn't even look like it is. Right? So there's a nasty question of how to decide, in general, how do I know if y can be solved for? Now, there is an even more subtle question. That's refinement here. This is business about local. And local says, look, I'm only interested in a neighborhood of the point in question. So if I'm looking at this point and I want to ask, can I view y as being a function of x? Locally means I get to ignore everything outside of my little neighborhood. And so I'm going to ignore all of that, and I'm going to ignore everything that maybe would come on the other side. I'm going to look just exclusively at that little piece of curve alone. And looking only at that little piece of curve, can I view y as a function of x? Now, in this case, yes, I can, because look, it passes the vertical line test, no problem. Likewise, very similarly, if I am looking at this point right there. A lot of people would say it's not a function because, again, it fails the vertical line test. Well, yeah, but if I look locally, only in that vicinity, then all I'm responsible for is, oh gosh, that's the wrong. I'm only responsible for just this little bit of curve right there, and that little bit of curve, fine and dandy, no problem. This is locally y as a function of x also. And what we're going to see next time is that there are some actual problems. The biggest actual problem is stuff like this point right here. And we'll see next time why that's a no and what that means. See y'all later. Have a good one. And don't forget about attendance if you came in after I finished.